Welcome to this video for MCET 450 Advanced Mechanics. In this video, we're going to continue to review basic statics problems. This problem that we have in front of us shows this system setup. And the statement says, calculate the magnitude of the force supported by each of the pins at A and B for the loaded bracket. So we always have a pinned constraint here at A and another pin at B. Of course, B is connected to a wheel, so it's like an axle. And as always, our first step in this analysis is to create a free body diagram. So we'll bring over our engineering graph paper, and we want to draw our diagram roughly to scale. So we can let each box on the paper represent roughly 20 millimeters. And so if we make our starting point here, then point B is 120 millimeters away, or 0.12 meters as the case may be. What we have here is an angular distance of 180 millimeters at 30 degrees. So really the first thing to do is to figure out what the x and y distances are, assuming that we're going to use a basic coordinate system. So we can write this right out on the diagram from the textbook, and we can translate it to our free body diagram. So what we basically have here, right, is a right triangle. And the hypotenuse of that triangle, we recognize, is 180. Thus, if we look at the 30-degree angle here, we know that the leg out here is the leg opposite the 30-degree angle. Therefore, the sine of 30 is equal to the opposite leg, we'll call that y, over the hypotenuse, we'll call that h. So therefore, we find that sine 30h equals y. So that means that we simply take the sine of 30 degrees and multiply by 180, and we'll have this y value right here. And the sine of 30 is 0.5, as you may recall. Therefore, y equals 90 millimeters. And then, similarly, if we look at the leg over here, we have the cosine of 30 equals, we'll call that x over h. And then if we simply cross multiply, we know that the cosine 30 times h equals x. So we can look up the cosine of 30, which is about 0.866, and multiply that by 180. And we find that x is equal to, we'll round it to 156 millimeters. Okay, and of course, we want to work in the base units, so we know that is 0.156 meters, and this is 0.09 meters. We come back to our free body diagram that we started, and what we'll find is that applying our scale that we already established of about 20 millimeters per block, if we come over in the x about 8 blocks, so it's pretty close to 160, and it doesn't have to be perfectly to scale. We'll come over 1, 2, 3, 4, 5, 6, 7, 8 blocks here. And then we'll come up 5.5 blocks, because that would be close to 90. So we come up 1, 2, 3, 4, 5, about half here. That's going to be our point A. So now we can create the radii that go around each of those points. We'll use my circle template here. That one looks close enough to use. So we have basically a half circle this way, and we come over to this point here. And we have a little bit of a circle. There's not a whole lot going on there if you think about how the radius is, but we'll just kind of draw that, and then we'll come up to this point here. And we have a good portion of a circle here. And now we'll just use tangent lines to connect everything up. So, got a tangent line here, and this would go up this way, up to there. And this one just kind of comes back down around and connects here. So now we've got our basic shape drawn roughly to scale. The next step in the process is to apply the forces according to the problem statement and then determine where the reactions for those forces will be. So the problem statement told us that we have a force on the far end of 1.6 kilonewtons. We'll just convert that to newtons because we want to work in the base units. So that's effectively 1,600 newtons. And then at point B, we're going to have a reaction normal to the application. Now, take back a look at the picture from the problem again. This is at a slope of 30 degrees, right? That means you're going to have a reaction coming in like this. So draw that on our free body diagram. That's about 30 degrees. Now, something to pay attention to, though, is to keep it consistent and so that our x and y coordinates work out very similar to how we solved them over here, your angle always has to come off the horizontal plane. Now, if you take it off the vertical plane, that's fine. You just got to switch your sines and cosines. If you're comfortable with that, that's fine. But I like to keep it consistent, and so therefore, I like to use the horizontal. This angle here is the complement of 30 degrees. Therefore, this is a 60-degree angle. That'll be important when we need to break our reaction into x and y coordinates. So, but that is going to be the reaction B, RB. This is point B here. While we're at it, this is point A up here. Now, again, we have to figure out the reaction at point A. And basically, because this is a pin connection, we know we're going to have a similar reaction relative to the angle that this is. So we're going to have an x and y coordinate for A and B. So it's probably a good idea, as we're starting to talk about this, to establish our set of coordinate axes, because we really haven't done that yet. So let's go over here. Establish that this is our set of coordinates, this is the y coordinate, this is the x coordinate. And now we can say that we're going to have a reaction to A in the y direction and a reaction to A in the x direction. And then which direction are these going to be going? Before we can establish that, let's look at the components of the reaction at B. Because we know the direction of that, we know it has to be pushing up and to the left. We know that the y reaction has to be going up. Add in. We'll call that R, B, Y. And we know the x direction has to be going to the left. And we'll call that one. It's a little confusing. Let me reposition these labels so we don't confuse ourselves. This will be R, B, Y, and this will be R, B, X. So now when we take a look at this and we see that we've got a downward force here of 1600 newtons, we've got RBY pushing up, we know that RAY has to be pushing down. And that's basically looking at the moments, right? So if we were to take moments about point B, and that means these forces cancel out because there's no distance from B, you would have this force rotating the body, or rather trying to rotate the body, counterclockwise, and therefore the reaction at point A would have to be rotating or trying to rotate the body clockwise. So they have to counterbalance each other. So that's how we know A is going down. Then, if we further look at this, we'll see that the only x-based reaction or force we have is RBX, and it's going to the left. Therefore, RAX has to be going to the right. So now we can label these RAY and RAX. It's a little messy there. Let me fix that. Now we've got our forces drawn out and we've got them properly broken into components relative to our coordinate system. Now we need some distances. So we draw an extension line right here. We were told that the distance from the application of the load to point B was 120 millimeters. So we can convert that to meters and call it 0.12 meters. And we also know a couple other things. We know that this distance now from B to A up here, trig that out, we know that is 156 millimeters, right? It would be 0.156 meters. And we also know the vertical height from B to A is 90 millimeters, so 0.09 meters. And just for good measure, we can drop in the hypotenuse of that triangle and say that this distance is 0.18 meters. So the next step in solving for our reactions is to set up our equilibrium equations. Remember, the equilibrium equations are as follows, for a 2D analysis, of course, as this one. Sum of the forces in the x direction have to equal 0. The sum of the forces in the y direction have to equal 0. And the sum of the moments about any point, and for our analysis we'll use point A, have to equal 0, and we have to specify which direction of rotation is positive, and we'll call the counterclockwise direction of rotation positive because that's the typical convention associated with mechanics problems. So this is a good time for you to pause the video and see if you can write out the equilibrium equations on your own. So I'll give you a moment to pause the video. Okay, so hopefully you've written out your equilibrium equations and see how they compare to mine. So take the sum of the forces in the x, and of course we only have two reactions, so we have a positive RAX and we have a negative RBX. Sum of the forces in the y, we have a positive RBY a negative, let's go over here, a negative RAY, and then a negative 1600 newtons. Now for our sum of the moments about point A. So we've got a couple things going on with our sum of the moments. Now the 1600 about point A is trying to create a counterclockwise rotation, so we consider that positive. So 1600 newtons, and that's being multiplied by the distance from point A, which we know is a 0.12 plus 0.156. That is 0.276 meters. So times 0.276 meters. And now, what else do we have going on? At point B, we can simply look at RB at a distance of 0.18. Now, we could use RBY and RBX, and that would work as well. But let's just use RB since it simplifies our equations a little bit. So that's trying to rotate about point A at a distance of 0.18 meters. So that would then, of course, be trying to turn clockwise. That's negative. So I'm just going to jot it down at the bottom here because I ran out of room on the right-hand side of my page. That'd be minus RB times 0.18 meters. So in the first equation, we have two unknowns, can't solve that. Second equation, two unknowns, can't solve that. But the third equation, we can solve. So let's solve for RB. So we'll take the RB times 0.18 meters and move that to the other side of the equation, right? It's basically adding it to both sides. And we got RB times 0.18 meters is equal to, now we have 1600 times 0.276. Let's do that math. So that's 441.6. And the units, of course, are Newton meters. We're multiplying, so we multiply the units. Newton meters. Now we can simply divide both sides by 0.18 meters. And that equals, RB equals 2,453. Now check our units. We have Newton meters divided by meters. The meters cancel out. We're left with newtons. So we know the reaction at RB. Now, to get the other ones figured out and find the net reaction at RA, what we will need to do is convert RB into the components. Let's do that over here. Remember, that's where this comes in, this 60 degrees. So RBX will equal the cosine of 60 times RB. And let's leave a space there. We'll say RBY equals the sine of 60 times RB. So we can solve this now. So the cosine 60 times 2,453 newtons. That equals, squeeze it in here, 1,226.5 newtons. Then we'll take the sine of 60 times 2,453 newtons. That equals 2,124.4 newtons. Okay, now we can go back And we can solve the sum of the forces in the y to find RAY. So 0 equals RBY minus RAY minus 1600 newtons. Therefore, we can plug in 0 equals, we now know RBY is 24.4 newtons minus RAY minus 1600 newtons. So we can take the RAY and move it to the left side, effectively adding it to both sides. That's going to equal 24.4 newtons minus 1600 newtons. And RAY, of course, then equals 524.4 newtons. Now we can do something similar for RAX. This is kind of an easy one. If we go to the sum of the forces in the X, give myself one more paper space here. Find that 0 equals RAX minus RBX. So effectively, RAX equals RBX. So that means that RAX is equal to 1,226.5 newtons. So now what we can do is we can figure out what the reaction at A is and at what angle it is applied. Know that if we go back to our free body diagram, let's jump up here for a second. We know that's going down and to the right, so we know it's going off in this direction. So it's basically going off this way. Move it off the diagram. And come down here, we have our RAY, which we said was 524.4. And we have our RAX, which we said was 1,226.5. Well, that's pretty simple to figure out what the reaction is because it's a Pythagorean theorem at this point, right? So we find, if we jump back down here, that RA is equal to the square root of 524.4 squared plus 1,226.5 squared. So RA is 1,333.9 newtons. But now let's figure out what the angle is that it's being applied. So again, we go back to our triangle that we drew up here. And if we want to know the angle, we can do it a couple different ways. But I like doing we'll do it off the horizontal, right? And then that's simply a tangent function, opposite over adjacent. So we take 524.4 and divide it by 1,226.5. Right? And we take the inverse tangent of that, or the arc tangent of that, right? That, jot in here arc tan. That equals 23.1 degrees. So if we come back down here, we can draw our vector direction like this and say that this is 23.1 degrees from the horizontal. It's important to understand how we get here because this is the net reaction at RA. So if we were going to analyze the stress in the pin at RA, we would use this force to find the stress. We wouldn't use the AX or the AY. We have to get the net reaction or the resultant reaction. So that's it for this video. Thanks for watching.